Welcome. Today we're going to talk about Chapter 3 on perception. And perception is essentially how our mind builds a representation of the outside world based on the information that it receives from the senses. So, as I already mentioned, perception is essentially how we experience the world. So, our mind builds a representation of it depending on the information that it receives from the outside world through our senses, whether it be light through our visual system, or sound through our auditory system, or the shape of things that you encounter through your sense of touch. And the basic concepts that it is important to keep in mind about perception is that it can actually be quite dynamic and change depending on information that's added after the fact. And it's a process that's quite complex. It's not a simple matter of just adding up a bunch of information. It involves a lot of information that you retrieve from memories, and in that sense, it's quite similar to other complex cognitive processes such as reasoning or problem solving. And it's important to also realize that our perception isn't a very static or passive process, but rather it's a part of a larger process that allows us to interact with the world. And so perception is heavily influenced by what we're going to do with that information and how we're going to use it in order to interact with the outside world. So let's start off by first considering why it's necessary for perception to be this more complex system that's more than simply just adding up the information that we receive from our senses. Let's start off by considering the example of how we receive visual information about objects that surround us. For example, the retina receives some kind of stimulation in the form of photons that bounce off of other objects in the world and then activate the neurons in the retina that then relay that information into the visual cortex. But it's important to realize that that pattern of activation on the retina can be somewhat ambiguous because multiple different objects can produce the same image on the retina, or the same object can produce the same object can produce different images depending on how it's oriented in space. So for example, if you have a square-shaped pattern of activation on the retina, it might be produced by a square object, but it can also be produced by a object of a slightly different shape that so happens to be oriented in space in such a way that it casts a square-shaped image of itself on the retina. And so our visual system needs more information in order to figure out the exact properties of the object that's causing that pattern of activation. Another example of a potentially ambiguous or difficult situation for a visual system to resolve is that objects can often be hidden behind other objects, either in whole or in part. And so when you're searching for them in a scene, you often need to rely on partial information that's available to you in order to infer what that object might be, just based on seeing a little piece of it poking out from behind something else. So, for example, here we have a magazine lying on top of a bunch of other things, and we can see some parts of them sticking out, and that tells us about the rest of the object. So, for example, if you were to look for scissors in this scene, you may be able to infer that they're underneath the magazine from the bit of the handle that's poking out. And so your brain would actually only know about that ambiguous-looking plastic object that's poking out from behind the magazine, but based on your knowledge of what the handle of a pair of scissors looks like, your memory essentially supplies the additional information that the brain requires in order to understand that the scissors are underneath the magazine, even though you can't actually see the majority of the object. And in fact, you can't see the most important part, which is the blades. And so identifying that object is done not only based on what the visual system receives from the outside world, but also from the knowledge that you have about what these kinds of objects typically look like. Another example of a situation where our brain is forced to work with incomplete information in order to still accurately perceive the world is if, for example, you're trying to recognize somebody, but you don't have the best view of them. So maybe you're looking at them through a frosted window, or you're simply looking at them from a relatively far distance where your vision doesn't have the best acuity. What ends up happening is that you don't get the clearest picture of their face, and yet you're still able very often to recognize them if it's a person that you either know personally and you have seen quite often, or if it's some kind of celebrity that you've seen often on television, for example. So here in the image on the slide, we can see some examples of blurred images, and yet it would be quite easy for most of us to recognize at least the majority of the people in these images. So, for example, going left to right, it's pretty clear to me that I'm looking at Will Smith, then Taylor Swift, Barack Obama, Hillary Clinton, Jackie Chan, Ben Affleck, and Oprah Winfrey, despite the fact that they're quite blurred because these are faces that I've seen quite often on television. And so my brain is able to use the partial information that's available in order to supply me with the answer that I need when I'm thinking about who it is that I'm looking at. Another example of a potentially ambiguous situation that the brain often needs to resolve based on the information that's coming in from the visual system is when it's trying to consider that the same object could appear differently depending on the direction that you're viewing it from. So, for example, here we can see images of the same chair but taken from different viewpoints. And so if your eye receives this information, obviously the chair, when viewed from these directions, would cause a very different pattern of activation on the retina. And yet the brain still needs to understand that it is still the same object that it's looking at. And so it needs to consider the physics of the world and what objects could look like when rotated and viewed from different directions in order to give us the understanding that we're still looking at the same objects, just from different viewpoints. And so I hope that the examples that we just took a look at make it clear that our perceptual system relies not only on the environmental stimulation that it receives from the outside world, whether it's sound or photons, it's the knowledge and expectations that we have from our own lived experience that our brain uses in order to interpret that information that's coming in. So there are potentially two ways of considering the way that perception works. The first is what's known as the bottom-up approach, where the root of everything is the information that's coming in, and then everything is built up from there. However, there is the alternative way of looking at it known as constructive perception or top-down processing, which is more in favor by modern researchers. And it really consists of what we've been talking about already, that the mind really constructs perception using both the information that's coming in from the outside world and your expectations about the outside world that are based on your memory and knowledge about the way that the world operates. A really good example of this is how a single outside representation of a visual object, so for example, the little blob you see in part A of the image on the slide, if we take that exact sequence of pixels and we put it into different contexts, the brain will interpret it in very different ways. So for example, in part B of the image, it's placed on something that resembles perhaps a coffee table or a dinner table. And in that context, if you're looking at it, you would probably interpret it as some kind of bottle or food container. However, if you place that exact bunch of pixels in a different image, like for example in C, you would probably interpret it as a part of that person's shoe. And in D, you would probably think that it's perhaps a person standing on the street, or in the case of an identical blob that's placed on the left side of that same image, you might think that it's a car. And so this is an example of the brain really constructing our perception of the exact same stimuli very differently depending on our knowledge of the different contexts in which we might actually perceive it. If we consider the way that we process sounds, and in particular language, we'll see that the exact same processes tend to work for sound just like the way that it does for vision. Now, I'm not going to spend too long talking about it here because we're going to have an entire separate chapter devoted to the way that we process language. But just to give you guys a brief idea, if we consider the way that we process a language that we are actually familiar with, that we're fluent in, our brain does a lot of this kind of top-down processing in order to make it meaningful for us beyond just the sequence of sounds that we're receiving. So, for example, if a person is speaking fluently, you'll still be able to segment their speech into the individual words and understand where one word ends and the next one begins, even if they're not making long pauses in between those words, because our brains are familiar with what kinds of words are present in that particular language, and will know that when the next word begins, that it has a separate meaning from the one that preceded it. And along the same lines, you'll be able to have a good accuracy in predicting which word or sound will follow the one that preceded it, because you have an idea about which kinds of words and sounds go together in that language and the sequences in which you'll typically encounter them. And so taken together, this gives us what we call the likelihood principle that also applies to vision, where we perceive the world in the way that the brain believes it to be its most likely configuration based on all the things that we know about a given language or the way that certain objects might appear. Now, I wanted to talk about the sequence in which various advances were made in psychology that got us to the point where we are today. Now, one of these earliest proposals regarding the way that perception is actually built up from our sensory experience was by Helmholtz, who proposed what he called unconscious inference, where he said that essentially whenever the brain receives a particular piece of information regarding the visual world, it uses the probability of what could have produced it in order to make inferences about the real state of the world. So, for example, if we look at part A of the image, we can see that that particular bit of visual activation that we would get in the retina can be caused by different things in the real world. So it could be caused by two rectangles standing one behind the other, and the red rectangle is partially obscured by the blue rectangle, and that's why it appears the way that it does. However, there's an alternate explanation that perhaps the image or the object in the back isn't a rectangle. Perhaps it's cut out in the outside shape of the blue rectangle, and it's this inverted L shape that's behind the blue rectangle. Judging by just what the retina receives, we can't actually tell those two possibilities apart. However, our brain knows what kinds of things it will often experience, and you've probably haven't experienced seeing floating blue, or rather floating L shapes, right, that are suspended in midair. So that would be an unlikely interpretation of what's going on in the real world. And so your brain will most likely interpret that image A as representing two objects that are standing one behind the other. However, it wasn't all early researchers in this area who were thinking of it in this kind of top-down processing approach. A lot of them were thinking more of in a bottom-up processing direction. So, for example, Willem Wundt, who we talked about briefly 2 lectures ago, he advanced the view that we call structuralism, where he believed that our perception is simply built up from adding up all the individual pieces of sensory information that come in, and there's nothing more to it than that. So, for example, if you look at the picture on the right side of the slide. So he would propose that our brain builds up the image of the human face based on simply the individual pieces of information that we receive from all the little features of the face. However, as time went on, people came to acknowledge that there was more processing taking place and that the brain essentially tries to perceive objects as a whole rather than simply the combination of different parts. And this is where we get the view of Gestalt perception, Gestalt being German for something that happens all at once. And in this view, the mind does group together all the patterns of information that it receives and processes them together according to certain rules that it has based on certain hardwired patterns of behavior. And what led some of these researchers to the realization that the brain must be doing something more than simply adding up sensory information is several actual experiments that were carried out that showed that the brain can create illusory information, meaning that it will introduce new information that isn't present from the senses. For example, Max Wertheimer showed using a stroboscope that if, for example, you turn on a light and then turn it off, and then after a very brief period of time, you turn on a light that appears the same in a different location, if that interval between them is short enough, the human mind will perceive it as one light that moved from one location to another, as opposed to two separate lights at two locations. And this is the same principle that allows us to see motion in video, because obviously when we're watching a movie or a show or really any kind of video, and we think that we see things moving on the screen, we're really not seeing any actual motion because we're just seeing a slideshow of frames replacing the one before it, and it's happening fast enough that our brain creates the illusion of motion. And this is a very good example of the mind essentially building up perception from more than simply the bits of information that it receives from the senses. And so the people who were advancing this view of Gestalt perception came up with several principles that they believed were built into the brain that allowed it to produce these kinds of processing approaches from the sensory information. For example, one of them is what they called the principle of good continuation, where you tend to view objects as a single large object as opposed to a collection of individual components. And a good demonstration of that is, for example, if you were to look at the picture of the rope in picture A, you probably perceive it as a single coiled piece of rope as opposed to a collection of individual separate pieces that are simply arranged in that way. And they believed that the brain simply has a natural tendency of making this assumption. And another similar principle is what they called the principle of simplicity. And here you basically assume that any kind of visual image that you perceive is most likely the result of the simplest arrangements of objects as opposed to a more complex one. So, for example, if you were to look at picture A, that's similar to the Olympics logo, you would probably perceive it as a collection of 5 circles, some of which are lying over top of the others, as opposed to interpreting it as the overlaps being individual pieces that are simply butted up next to the others, like you would see in part B. And so the brain tends to assume that you have a situation that can be explained in the simplest terms as opposed to going for more complexity. Another of these principles is the principle of similarity, whereby the brain will group together objects based on how similar they are to their neighbors. So, for example, in picture A, you would probably see this as a square grid of red dots, whereas in picture B, you would most likely see it as a series of columns with alternating blue and red dots, And your brain naturally groups them together based on the color into these columns, as opposed to picture A, where they all share the same color, so that the brain doesn't have any reason to group them as individual columns as opposed to one single grid. We can also see this in this example of a photograph of a woman standing on the beach, where it almost appears as though her head is floating, because it so happens that her skirt matches the color of the sand around her, and her jacket and shirt match the color of the water and foam of the sea. And so because they blend together with the background, they are perceived to be as part of the background as opposed to part of the woman that's standing there. And so to summarize, the principles of Gestalt perception are that you have these specific mechanisms that the brain has for organizing information that are more or less built in or hardwired in, and that the role of experience is actually quite minor, and that the brain really relies on these very specific ways of processing information. And although experience can influence perception, they believe that it only plays a very minor role. And also, they didn't really believe that these principles of perception can really be modified by experience very much. So they didn't really value the role of neuroplasticity in modifying how the brain uses prior information in order to interpret sensory stimuli. Now, getting back to top-down perception, another way that our brain could be actually configured in order to do some kind of processing on the sensory information that we received based on, our experiences with the world, is by considering the regularities in the environment that we observe all around us. Now, one such regularity is that, for example, things that are more or less horizontally or vertically aligned tend to be much more common in the environment than things that are off at various angles. And this produces the oblique effect, where the human brain is much more sensitive to stimuli that are horizontally or vertically aligned versus those that are at various diagonals. And we can demonstrate this experimentally by, for example, showing people two bars that one might be slightly off from the other by a few degrees in its orientation. And if they're both diagonal, people have a harder time telling whether they are perfectly aligned with each other or whether one is slightly off, than versus if one of them at least is perfectly aligned vertically or horizontally. And if the difference between that bar and its neighbor is, again, very, very slight, it's much easier for people to tell that one of them is slightly off if the other one that they're referencing it is perfectly horizontal or vertical, versus if they're both slightly off from the vertical or horizontal orientations. Another such regularity that we could learn from the environment is what's known as the light from above assumption. So this is something that our brain tends to do because almost everywhere you look in the environment, lights tend to be positioned above us. So if you're outside, the source of illumination, whether it's sunlight or starlight, is coming from above us. And if you're indoors, usually we place all the lights, artificial lights that we have, on the ceiling. And because of that, our brains essentially learn that light tends to come from above. And so the way that it interprets shadows is by always assuming that unless it's really clear that something else is going on, any situation where it's a little bit ambiguous, the brain will assume that the scene is being illuminated from above and will interpret depth and shadows and things like this based on that assumption. And here we have a good illustration of that light from above assumption. If we look at picture A, it looks like sand on a beach that somebody has been walking through, and that these bits of shadows are because the sand has impressions in it, perhaps from somebody stepping on it. And this makes sense if we assume that the light is coming from above. And these divots look like actual impressions that are pressed into the surface. However, if we were to take that picture and flip it upside down, like we have in example B, suddenly they don't look like something is pressed into the surface, but rather that these now look like little mounds that are sticking out of the surface, even though it's the same image, because our brain interprets the way that the shadows are cast now as being indicative of these are things that are sticking out of the surface and are therefore casting shadows in the opposite direction if the light is still coming from above, which our brains naturally tend to assume. And of course, our brains will factor in our knowledge about what kinds of things belong together in particular places, right? So we mentioned this in lecture 1, where our brains will use our knowledge of what belongs in particular locations, what are known as scene schemas, in order to try to process the objects that are in them more efficiently. So as we talked about in the example earlier, if you see an object that tends to belong in a particular scene, so for example, some bread that would typically belong in a kitchen, if you show someone that scene, it makes it easier for them to interpret the object, to recognize that object, as opposed to other objects that would typically not belong in that scene. So, for example, the drum or the mailbox that definitely don't belong in a kitchen. Another way of thinking about how the brain combines information from the senses with information that the brain already holds about the way in which the world works is by using Bayesian statistics. This is named after Thomas Bayes, who was a mathematician, and he came up with what we call Bayes' theorem, and it is essentially a formula for calculating how the probability of an event, along with its magnitude, produce an impact at the end and how likely it is. In general, this is a way that essentially we have of updating information about the world as new information is coming in. I'm not going to get into the details of the calculation, but just roughly speaking, concept is such that we have some prior, right, some knowledge about the way that the world is. We have some kind of information that tells us about the likelihood of a particular event, right? And then we decide whether that event could actually take place based on our understanding of its likelihood and our prior, right? Combining these two things together. So to use the example that the book gives us, imagine that you come across somebody who's coughing. Now, you may have some prior information about the kinds of things that could produce a cough and some information about how prevalent these things might be. So, for example, you may have an understanding that, a cough could be caused by somebody having a cold or lung cancer, but probably isn't caused by something like heartburn. And you also have this prior knowledge about the frequency with which these things might occur in a random person, right? So colds are pretty common, heartburn is pretty common, but lung disease is pretty rare. So then you're able to combine these two pieces of information, the fact that the cold could be caused by the cough could be caused by either a cold or lung disease, with the information that colds are much more common than lung disease, in order to give you the answer that the reason that this person that you encountered is coughing is more likely to be caused by a cough than by lung disease, and very unlikely to be caused by something like heartburn, which you know to be very unrelated to coughing. So to review the different ways that we have of thinking about the ways in which the brain actually builds our perception of the world based on the sensory information that we have coming in from the outside, is that we have multiple top-down processing approaches, including unconscious inference, including using environmental regularities, and Bayesian inference. And as an alternative to that, we also have the idea of Gestalt perception, which is a more of a bottom-up approach, because the people who advanced it believed that the brain was more dependent on built-in structures and sensory information than on using experiences and knowledge in order to build our perception of the world. Now, as you can imagine, some of the networks of neurons that the brain uses in order to do this kind of perceptual processing will over time become attuned to some stimuli that the brain processes frequently in particular patterns. So we already talked about the example of the brain becoming more sensitive to perceiving horizontal and vertical objects in the world because those are the kinds that you would frequently encounter in nature. And this is an example of the plasticity of the brain essentially allowing it to tune itself to the kinds of stimuli that the individual will encounter more often. Another good example of this are the neurons in the fusiform face area that we already talked about in the previous lecture that become attuned to perceiving faces because we see them very often in the environment around us. However, it's important to note that this attunement happens in terms of the kinds of stimulation that these neurons receive, and that they do have a propensity for responding to stimuli that fit certain criteria. So, for example, there was a study that tested the idea that what if we produced another class of objects that shared the typical properties of faces, that they have a certain template that they follow, but there are a number of variations within that template. So scientists created this class of objects that they called greebles that all had a similar configuration of parts, but that those parts could vary in lots of different ways, just like human faces. And what they found was that when they were testing people and recording their fusiform face area levels of activity in the brain, they found that initially this area of the brain would respond very strongly to faces and not very strongly at all to these greebles. But with training, so as they were exposed to more and more of the variations of these greebles, these neurons actually became attuned to them as well and started to respond to them much more strongly than they did before, indicating that through neural plasticity, these neurons that had previously been specialized just to faces were now being used by the brain to also classify these greebles because they fit the kinds of stimuli that faces would represent. Another good example of neurons being attuned to a specific class of stimuli are neurons that respond to certain kinds of motions. So, as you can imagine, from an evolutionary perspective, it's very important for us to be able to spot other animals moving because they could represent a source of food or they could represent a source of danger to us. And so we have neurons that respond very strongly to any kind of motion that's similar to another animal moving. And we can demonstrate this by seeing that this group of lights doesn't really look like much of anything until we bring it into motion. So when I play this video on the right side, you will see that actually it becomes very obvious that this is a point light display of a person walking based on just this very tiny amount of information, because we have neurons that are ultra sensitive to anything that would indicate to us that there is an animal that's moving. And speaking of motion, it's also important to realize that our perceptual systems are very much in tune with the way that we move our own bodies, because ultimately the reason that we need to understand what is happening in the outside world is in order for us to interact with it effectively. And so our perception system is involved in almost every stage of us actually planning and executing any kind of motion. So for example, if you wanted to pick up a cup of coffee, you would first need to use your visual perception to identify where that cup is. Then you would need to use it to guide your hand towards that cup and grasp it. And one important piece of information that is a part of any kind of planning of motion that we do with our own bodies is understanding depth, right? So the distance between ourselves and other objects in the environment, such that we can actually use that information in order to reach for them, to catch them if they're in motion, or to avoid them. And there are two types of cues that our brains are using in order to judge depth. Now, the first group of cues is known as kinetic cues. And this is based on things like visual expansion, for example. So objects appear larger as they get closer to us. So if an object is approaching us, the image that it casts on the retina will get larger over time. And we can use that to judge how closely, or rather how quickly, it's approaching us. Another thing is motion parallax. So the best way of illustrating this is to think of if you're sitting in a car that's moving and you're looking out the window, you'll notice that things that are closer to you cross your visual field or appear to cross your visual field much faster. So, for example, if there are, trees or bushes lining the side of the road as you're driving. On the other hand, things that are further away from you in the distance, so for example, like hills or buildings that are further away, they'll appear to cross your visual field much slower as you're driving past. Now, the other group of depth cues are static, meaning that they don't require motion in order to work. So one very obvious one that I think I already mentioned before is binocular disparity, where the brain will judge the difference between the two images that it receives from each retina in each eye, and those differences will be more exaggerated the closer an object is to you. So if you were to hold up a finger in front of your face and then close one eye and then open it and close the other one, you'll notice a big difference in where that finger appears to be because it's positioned differently relative to each eye. However, if you were to do this with an object that's on the other side of the room from you, you'll probably notice that the difference is very small, if there is any difference that becomes apparent. And that's because the eyes are positioned further away from it, and so the difference between the two images that they received is much smaller than for an object that's very close to you, and the brain is able to use those differences to judge how far away things are. Another cue that it can use is the texture gradient, where you will be able to see much more finer details in things that are closer to you. So if you were to look around the objects that surround you, you can see much more fine details as opposed to things that are further away, and your brain will take that to be an indicator of how far or close things are to you. And then finally, linear perspective is another very useful tool that the brain uses. So if you have any kinds of parallel lines, they'll appear to converge in the distance, whereas closer to you, they'll appear to be further apart. And once again, the brain will use this information in order to judge depth and distance. Other things that the brain can use to judge distance when it's looking at collections of objects is interposition. So, for example, we know that objects that are closer to us can obscure objects that are further away. So if you have something that's standing behind a different object, it will be partially hidden, if not completely hidden. And so when we see several objects in front of us, like for example, these billiard balls, we can infer that, for example, the blue ball is behind the black ball because the black ball is covering up a part of it. And to keep using this example of the billiard balls, if we have information about objects' real size, so we know that in real life, these billiard balls have the exact same size, and so the fact that some of them appear to be smaller when we know that they're in fact the same size is used by the brain to infer that these ones that look smaller must be further away. And this is the relative size disparity. The next thing I wanted to talk about is the way in which the brain organizes information from perception by the way in which it intends to actually use that information. So we've been able to identify two distinct paths along which the brain sends this information from the occipital lobe, from the visual cortex, if we're talking about visual information, onwards to the frontal lobe. So, for example, we have the what pathway that is used to identify objects, and it flows along what we call the ventral pathway through the temporal lobe, through the bottom part of the brain. We also have what we call the where or the action pathway that goes along the dorsal part of the brain, so through the parietal lobe, and the information going that way is used to determine the location of objects and how to interact with them. And we have many experiments that were used to determine these two pathways. And one of these key experiments was done in monkeys that were trained to do two separate tasks. The first task was an object discrimination task, where monkeys were trained to always look under a certain object where food would be hidden. So, for example, underneath the purple triangle on the left side of the display that was put in front of them. However, after they had a piece of their temporal lobe removed, that disrupted their ventral perception pathway, meaning the what pathway that they would use to identify objects. And suddenly they had great difficulty locating the food because they were less able to remember which object was the one that was hiding the food underneath it. They were less able to identify it. On the other hand, the second task that monkeys would be trained to do was the landmark discrimination task, where the food was still hidden under one of two objects that were placed at opposite ends of a display in front of them. But instead of the two objects being different, they were the same, and the location of the food was indicated to them by the position of a third object that was placed closer to the object of the first two that was hiding the food. So in this example here, the food would be hidden again under the left object, and the monkeys were trained to judge this depending on where the cylinder was. So the cylinder in this example is closer to the left object, so the monkeys would be trained to look under the left object because it's closer to the cylinder. And the monkeys that were trained in this task, some of them had the parietal lobe partially removed, and that disrupted the dorsal pathway, the where and action pathway. And after that part of the brain was removed, they were suddenly a lot worse at doing this task because they were worse at being able to judge the location of the cylinder and were then confused about where the food would be. We also have information from human patients regarding the existence of this where and what pathways. And one very good such example comes to us from Milner and Goodale, who studied a patient usually referred to by their initials, DF. And this patient had a brain trauma to her temporal lobe, which disrupted her what pathway, her ability to identify objects and perceive their precise nature in space. And when she was asked to orient a card to a particular reference orientation, she had a lot of trouble doing it. So we can see on the left example, we can see how normal, or rather healthy control subjects, they were able to very quickly position the card that they were holding to, for example, a vertical reference in very few tries, and they were pretty accurate. However, if we looked at how DF did, you can see she was trying it every which way, and she was never very certain that she was doing it correctly. On the other hand, when the task was changed from just positioning the card and matching its orientation to actually putting it through a slot, and this is the example shown on the right side, we can see that suddenly DF became almost as good as the healthy controls, and it took her very few tries to do this. And this is because she was now using the where, or the action pathway, that goes through her parietal lobe that wasn't impacted by her injury, and therefore she didn't experience any difficulties in this more action-based tasks, as opposed to doing it simply in her hand, which didn't involve interacting with the slot that she had to put the thing through. And so in that earlier version, she was only relying on her vision of the reference orientation and her vision of the way that she was holding the card. So that was less action-oriented, and therefore she had to rely on just the accuracy of her perception of orientation, which was in fact disrupted by the damage to her what path. Another neat illustration of this distinction between the where and what processing pathways is by using the Ebbinghaus illusion. Now, the Ebbinghaus illusion that's illustrated in picture A is the illusion that if you take two identically sized objects, so in this case, the two circles in the center of each group of other circles, the one that's surrounded by smaller object than itself, so the one on the left, will appear to be larger than the one on the right that's surrounded by objects that are bigger than it. So if you look at this picture and you look at the central circles, chances are you will think that the one on the left is bigger than the one on the right, even though they're identically sized, and it's the objects that are surrounding it that are producing this illusion. Now, as you can imagine, this illusion is produced by us processing just what we see in front of us, and this uses the what pathway. However, the where pathway is completely unaffected by this illusion, and we can demonstrate this because if we asked people to simulate reaching for that central circle as if they were going to pick it up, and then we measure how they space out their thumb and their index finger, we'll see that they actually open the thumb and index finger to the same distance regardless of which objects they're reaching for. So the where pathway that is involved here, right, because we're using this information for action, is completely uninhibited by the illusion and is acting as though the illusion isn't happening. And in fact, when this illusion was tested by showing it to that same patient, DF, who was experiencing worse processing in her what pathway due to her brain trauma, she behaved in this task just like all the healthy people that this was shown to. So once again, her where pathway, her action pathway, was completely unaffected by her trauma because it takes place, or it goes through the parietal lobe and not the temporal lobe. And that's everything that I wanted to talk about with respect to Chapter 3 on perception. In the next lecture, we'll be talking about attention. That's Chapter 4. So please go ahead and read that chapter ahead of our lecture if you're able to.